Hello everyone, I'm Yifan Wang from University of Florida. I'm glad to present our paper LiDAR, an efficient high-dimensional learning index for large-scale dense passage retrieval. First, the passage retrieval means to retrieve the relevant passages to given query text. The typical application is search engine. So you type in some query keywords, and the search engine will return you the relevant documents. The state-of-the-art passage retrieval usually called dense passage retrieval, since they use dense neural embeddings to represent the text, like word-to-vec embedding and BERT embedding and so on. So the third space is the document embeddings, and for each query, first the query embedding is generated, and then the top key closest document embedding to the query embedding will be retrieved as answers because we think the closest embeddings means relevant. The issue is the k-nearest neighbor search, which is to search the top k. It takes uh, uh, it takes more than 50 times of the time than the query embedding inference. So the k-nearest neighbor is efficiency bottleneck in how search precise. Let's first introduce the k-nearest neighbor and approximate k-nearest neighbor. So k-nearest neighbor is to find the top k closest data points to a given query in the data sets. And the approximate k-nearest neighbor, also called ANN search, it also returns k points, but that may not be the exact top k closest points. There could be some relaxation for speed up. So in this paper, we focus on the approximate k-nearest neighbor, that is the ANN search. So there have been many typical ANN index, like LSH based, like product quantization and inverted index based, like graph based. But can we have new index type with higher efficiency? And our answer is the learning index. So the original learning index is used for one-dimensional data. So usually there is an underlying sorted data array, which is one-dimensional and sorted by the keys. And in the traditional index, like the B tree, the query key is looked up by the index to find the position of the key and retrieve the data. But in learning index, the index structure is a learning model, which is usually a regression model. The regression model will predict instead of looking up the position for the key. So the advantage is it is very fast because theoretically it only takes O1 time to predict, and it can be further accelerated by GPU. But the shortcoming is it cannot make sure 100% accuracy. So, but in our case, learning index is suitable for AN because AN doesn't require 100% accuracy. The issue is there is no existing learning index for very high dimensional AN search. Most of them are for low to middle dimensional, like less than 100 dimension. And our contributions includes we proposed one of the first learning index for AN search on very high dimensional data. And we also propose one of the first solutions that use learning index to solve dense retrieval. And we design clustering-based two-layer architecture to optimize the overall performance for the system. And we also have innovation on the several individual components, like extended SKSH, like key rescaling and RMI. So first, I will introduce some important relations. The recursive model index, also called RMI, it is a hierarchical structure of multiple ML models, and the search key is passed layer by layer until the final layer outputs the predicted position for the key. So basically, it is a deep regression model. And then it's the sorting KSH, SKLSH. So this method define linear order to sort the hash key from SH, and by which it preserved the raw data similarity. So the near data will be placed into the neighborhood on the hash key array. And so SQL will search like this. Given the query, it will first find the closest position on the array for the query by the hash key. And then it do expansion, that is searching the neighboring positions to find enough candidates and return to verify as answers. And it usually deploy multiple hash key arrays to improve the recall. And then it's our approach, LiDAR. LiDAR is constructed based on multiple basic units, which we call core model. The core model includes three modules. The first module is extended SKSH or ESKSH. It is for hashing and sorting the embeddings. Basically, it is for dimensional reduction to reduce the embedding into one-dimension hash key string. And because the RMI only accepts one-dimensional input, and so that's why we use such a module. And then RMI is the learning model to predict the position, and key rescaling is a module that we use to batch to interact with ESKSH and RMI. And first, the document embedding will be passed to the ESKSH, and from which they will be hashed and sorted into sorted arrays. And then the query embedding will also pass through ESKSH, and then the hash keys will go into the rescaling module, and then you input to the RMI to predict the closest position, and finally do a parallel expansion on the underlayer sorted arrays to find the candidates. And in the higher level, we construct a clustering-based architecture to organize all the core model. So we cluster the whole search space, and in each subspace, in each cluster, we build a core model, which is called in-cluster retriever, to index the subspace. And in one layer higher, we organize all the cluster centroids and index them using one more core model, which is called centroids retriever. And in one search, the query is given into the centroids retriever to retrieve the closest centroids to the queries. And then in each of the selected cluster, the in-cluster retriever will do their work to retrieve the candidates, and all the candidates will be merged as the final candidate to be verified. So by this architecture, we reduce the subspace for RMI to more effectively fitting, and can save the memory space and also increase the search speed because the in-class retriever are independent from each other, so they can parallelly doing their work. And next would be our individual components. First is the extended SKSH. So we extend it to cosine similarity, and we extend its way to sort hash keys, and we improve the parallelism. So originally SKSH search for the hash key arrays iteratively, but now we do it parallelly. And here is the important notation H is the number of hash key arrays. We will use it later. And then it's the RMI query scaling. So query scaling, it is created because RMI requires numeric input. So we have to convert each hash key to a numeric value. Because each hash key can be seen as a binary number, but it is too large because the hash key is usually long. So the binary number would be a bad training input for RMI. So we use rescaling module to do a min-max normalization. And surprisingly, after the rescaling, we found that the training data has become a linearly distribution. So we simplified RMI to using all linear regression models, and this have helped improve the predicting speed. And our experiments, we use two data sets, MS Marco and Wiki 21 million, and they both have thousands of queries to test. And we have several baselines. One ground truth, the exact KN, and PQ based baselines, and LSH based and SKLSH. And the evaluation matrix includes MRR and NDCG for effectiveness, and average query processing time (AQT) for efficiency, and distance cosine similarity. So first, the end-to-end retrieval quality, we can see LiDAR achieved the highest score, especially on the largest data sites. And for the retrieval efficiency, the light figure is the fixed parameter baselines. So the same parameter for each baselines on different size of data sets. We can see along with the increasing data set size, LiDAR has the slowest growth of the AQT. It means LiDAR has the best scalability. And the right figure, it shows the speed quality trade-off evaluation on the largest data sets. So we can also see the red line, the LiDAR's curve, it achieves the best speed quality trade-off. And then we evaluate some specific factor, like the H in ESKSH. So H is the number of Hashkey arrays. We can see uh, when H is not too large, increasing H will increase in MR while the search time stands still. For example, from H from 32 to 48. This means our parallelism works well, and it can effectively increase MR with a very tiny sacrifice on the search time. But due to the limited number of CPUs, when H is too large, like 64, the time is unavoidably increased. And then is the impact of the key scaling module. So here we define three kind of predictions. The first prediction is out of range predictions. It's the predictions that are not in the range 0 to the number of embeddings to be indexed. And the second prediction is the large error predictions, whose error is larger than 100. And the overlap prediction is the overlap between above. That is the large error predictions caused by the out of range. So we can say when we enable key rescaling module, both of the out of range predictions and overlap predictions are almost eliminated, and the large error predictions also be reduced very significantly. So it means the key rescaling effectively reduced the predictions with large error by almost eliminating the out of range predictions. So it proves the effectiveness of our key rescaling module on the overall quality. And finally, it is the memory footprint and construction time. So uh, by comparing LiDAR with the original SKSH, we can see LiDAR saves at least 50% space comparing to the original or flat SKSH. And in LiDAR itself, the in-class retriever, they takes the most space. That is intuitively. And we also see the bottleneck or the cost for LiDAR to save that much space is the uh, index construction time. It takes about two times construction time more than the SKSH. So that would be a problem we will solve in the future work. Okay, that's it. Thank you for watch.